Okay, Assalamualaikum and good morning. Sorry about the technical error. So please switch on your camera. So I will restart again my lecture session. Okay. Okay. So everybody can see my screen. Boleh
Yes,
nampak?
sir.
Boleh nampak,
Boleh aja.
Okay. So just now I've explained that if you want to change a value into a decibel, so we need to do 10 log of x. So we're gonna get a value in decibel. Okay. So I want to show the example. Okay. For example, 100. If you want to change into decibel, that means we need to do 10 log of 100. So this one you will get 20. Okay. Ini boleh cuba guna calculator. 10 log 100. You will get 20. So what's the value? The value in terms of decibel. Okay. Remember to write the unit dB. Okay. If you don't write the unit dB, that means your answer is wrong. Okay. Another thing is that we have learned last week we have learned about Dbw Decibel Power. Okay. Remember that power. Okay. If you want to change power into dB, to decibel, so what we need to do is 10 log power divide with the P reference. Okay, P reference. So if I want to make it, if I want to change power into dBW, for example, what I need to do is 10 log power divide with 1 watt. Okay, so I will get a value in terms of dBW. Okay, I will get a value in terms of dBW. Another thing is that 10 log power divide with 1 milliwatt. So I will get the value in terms of dBm, dB milli. Okay. And if I want to change into dB micro, 10 log the power divide with 1 microwatt. So I will get in terms of dB micro. Okay. So the key point here is you need to see about the reference. Okay. If the reference is 1 watt, that means we will produce dBW. If the reference is milli, we will produce dB milliwatt. Okay, remember here is dB milliwatt over here. Dia bukan milligram, it's not milligram, millimeter or whatever. It is a dB milliwatt. Okay, and then if you want to produce a micro, that means the reference value here is micro, and we will produce a value in terms of dB microwatt. Okay, so that means if you see from here, from this bracket, the above bracket, okay, the above bracket here, That means we want to produce the value over here in terms of watt. The value of here we want to produce in terms of milli, and the value in the bracket over here we want to produce a value in terms of micro. So that's why we divide with the reference value. Okay, so what you need to do is you need to always practice how to calculate this dB, dBw, dBm, and also dB micro. Okay, so in the test later, these kind of questions gonna come up in the test and also in the final maybe. So you need to practice how to calculate this one. Okay, and for example, maybe we need to do some example. Okay, so for example here 100 watt for example. Okay, kita ambil contoh lah. For example, I have a 100 watt. Okay, so I can change this one into dBw. So 10 log 100. So 100 watt, 1 watt. So it is 100. So what I will produce is berapa ni? 20 dBw. Okay. And then if I want to make it in terms of dBm, for example, 10 log 10 log 100 divide with 1 milli. Okay, 1 times 10 power of minus 3. This is 1 milli. Okay, so you can divide first this one. So
50
berapa?
50 dB milliwatt.
dB milliwatt, yeah. Okay. Yeah, so you akan dapat 50 dBm. Ni boleh cuba semua orang cuba supaya you faham macam mana nak kira So I hope that you try using your calculator now. So now let's try to change it into dB micro, for example. Okay, kita nak cuba dB micro pula. So therefore 10 log 100 watt divide with 1 microwatt. Ini berapa? 100 bahagikan dengan 1 micro. Okay, and then 10 log. So you get this one 80
80
dB micro.
dB micro. Very easy, simple. Okay. So if you have questions, you can ask. Okay, you can interrupt me. Okay, if you have question, you can interrupt me. You can ask questions. I will try my best to give the best answer to you. Okay, so I will proceed with the next slide. Okay, last week we have learned up to example 1.7. Okay. So example 1.7. Yeah, example 1.7. Okay. For a three-stage system with input power P in is minus 20 dBm, and the power gains of the three stages are 13 dB, 16 dB, and minus 6 dB. Determine the output power. Okay, so I want to draw it here. Saya akan lukis di sini. Okay. So the question said that we have three cascaded amplifier. Okay, we have three cascaded amplifier. So I will draw the cascaded amplifier, this one. Okay, and the question said that the value of the gain is 13, 16 minus 6. Okay, 13, 16. So A1 is 13 dB, A2 is 16 dB, sorry, A3 is minus 6 dB. Okay, and okay, so three-stage system power. Okay, so the question doesn't say this is an amplifier. Okay, so what you can do is so my drawing, maybe I will uh, change my drawing. Okay, so the question say that there are three cascaded systems. It doesn't mention about whether this is amplifier, whether this is a loss system or whatever. Okay, but you can see based on the decibel values. Okay, if it is positive decibel, that means it will produce gains, and if it is gains, that means it is amplifier, and if it is a negative value, that means it is a loss stage. Okay, so maybe I will revise my drawing. Okay, so I make it like this. Okay, so this is number 1, number 2, and also number 3, and the question gives the input as minus 20 dBm. Okay, so the input here, input power is minus 20 dBm. And the question asks, how much is the output power? So we don't know. Okay, and if you read again the questions, the question wants you to write in terms of the output power in terms of dBm and also in terms of milliwatt. So how to do this? So P out. So if you remember that we have learned previously, P out, sorry, A total is equal to P out divide with P in. Okay, this is what you have learned in the slides previous weeks. Okay, but this is only true if we use absolute value. Okay, these equations can only be done using the absolute value. However, the questions here said in terms of decibel and dBm. Okay, so let's do the first questions. The first questions asks how much is the value in terms of dBm. Okay, so P out. Yeah. So P out in terms of dBm. So this is again, you need to see that we need to calculate. So this is how much. Okay, so first of all, we need to calculate A total. Okay, so A total. Okay, if you remember in the previous slides, how we calculate the A total is that A1 multiplied with A2 multiplied with A3. Okay, yang kita telah pelajari sebelum ini ya. Okay, however, if this is in term of decibel, okay, if this is in term of decibel, we need to do something else. A total in dB, okay, what we need to do is A1 dB plus A2 dB plus A3 dB. Okay, so that means a multiplication process in the absolute value is done with the a multiplication process in the absolute value. It is a summation process in the decibel. Okay, so proses multiplication dalam absolute value adalah bersamaan dengan proses tambah dalam decibel. Okay, so you see that here. Okay, so what I need to do is 13 dB. Okay, sorry. So 13 dB plus 16 dB plus minus 6 dB. Okay, so this is equal to 23 dB. A total. Okay, and then if you don't understand, you try to ask me. Okay, so what I want to show you here, that multiplication process in the absolute value, it is equivalent to the summation process in decibel. Okay, so therefore when we want to write the P out, remember P out, so this is A total. If we use the absolute value, that means this is A total multiplied with the P in. However, if this is in term of dBm, okay, sekiranya ini adalah dalam sebutan dBm, P out in term of dBm. Okay, so you see that normally we do this kind of brackets. So A total in term of dB. So this is multiplication, so here must be plus. And this is P in. And remember, P in must be in term of dBm. Okay, so if this is here is dBm, over here must be dBm. Okay, so therefore here, so okay, before that, if the value here is dBw, over here you must do dBw. If here is dB micro, that means over here also must be dB micro. Okay, dia mesti sama. Okay, so therefore here you can write 20.
Doctor,
Yeah.
just one person has
Okay,
raised
okay.
hand.
Okay.
Azura ada benda nak tanya, Doktor.
Ya,
Dia
boleh
angkat
silakan.
tangan tadi.
Ya, silakan.
Okay.
Siapa ada soalan boleh terus tanya. Sebab kalau you angkat tangan saya tak nampak. Saya cuma nampak skrin. Okay.
Azura, unmute your mic.
Oh my doctor, it's okay.
Okay.
Saya nak cakap yang ada orang nak masuk kelas tadi.
Oh, okay, okay, no problem. So kalau if someone want to speak, no need to raise the hand because I cannot see the hand. Saya nampak skrin saja. So you boleh terus cakap lah, no problem. Okay, tak ada masalah. You can interrupt me, okay, no problem. So I will proceed this one. So 23 dB plus. So the input is given as minus 20 dBm. Okay, input diberikan sebagai minus 20 dBm. So here is minus 20. Okay, so in this case you can just subtract, no problem. Okay, 23 minus 20, so you will get 23.
3 dBm.
Yes, 3 dBm. Okay, so this is the first one. So the second question asks, okay, let's do the second question. So the second question asks, what is the output power in terms of milliwatt? Okay, the second question in terms of P out in terms of milliwatt. Okay, so in this case you need to change the whole thing. Okay, in this case you need to change the whole thing, or you just need to convert. Okay, so I will show you the difficult part. Okay, okay, so what you need to do is you need to change the value of decibel into absolute value. Okay, so ni boleh try ya. Anti-log 1.3. Okay, sebab you kena bagi 10 dulu ya. You need to divide with 10 and then you can do the anti-log. Okay, so this is 19.953, 19.953, and this one is anti-log 1.6. So 39.181, 39.81. Okay, and this one is minus 0.6. So 0.251, 0.251. Okay. And how much is minus 20 dBm? Okay, so if you do direct conversions into absolute value, so that means this one anti-log minus 2 you akan dapat dalam milliwatt. Okay, so if you do anti-log minus 2, because we need to divide with 10, remember 10 log power, so we need to divide with 10, so therefore it becomes minus 2. So anti-log of minus 2, you will get 0.01, but the value, remember, in terms of milliwatt. Okay, so yeah,
Doctor, I have one question. How to get 19.953? I mean the formula.
the formula. Okay, so
Okay.
so I show here. So 10 log 10 log A1, so you will get in term of dB, right? So 10 log A1 you get 13 dB. So you need to divide with 10, so log A1 is equal to 1.3. Okay, sorry, we cannot use here, so just put 1.3, no need to put dB. So therefore A1, so therefore A1 is anti-log of 1.3, which is 10 power of 1.3. So ini you boleh guna calculator 1.3. So you get 19.953. Okay, saya teruskan.
Boleh doktor, thank you.
Okay. So now we need to so I will find the A total. So how to calculate the A total? A total is equal to A1 multiplied A2 multiplied A3. So this one is 19.953 multiplied with 39.811 multiplied with 0.251. So you will get this. How much? Ni boleh try kira. So 19.953 multiplied with 39.811 multiplied with 0.251. So you will get 199.382. So 199.382. A total. Okay. And then how much is the output power? So P out is equal to A total multiplied with P in. Okay, so this one is 199.382 multiplied with 0.01 milliwatt. Okay, 0.01 milliwatt. So you will get the value. 199.382 multiplied with 0.01. So you akan dapat 1.9938 1.99.
Doctor,
Yeah,
again one question.
yeah,
For P input,
yeah.
how to convert the, I mean, it just seem like convert dBm, I mean 13 dBm tu ke? Yang dapat 0.01 tu.
Ini, okay.
This one. Sama juga macam tadi ke or beza sikit dia punya formula?
Sama macam tadi tu maksudnya?
Sama macam tadi tu, I mean how to convert milliwatt tu.
Okay. So I will show here. So you see that 10 log. Saya tunjukkan je. So 10 log power divide with 1 milliwatt. Is you will get minus 20 dBm. Okay. So here is 10 log of power P divided with 1 milliwatt. So this is minus 2. Okay. So if you do anti-log of this, okay, kalau you buat anti-log ini adalah bersamaan dengan anti-log minus 2, 0 point. So you akan dapat this one also. P is equal to 0.01. But remember, this is in terms of milliwatt. Okay. So ini sebenarnya dalam sebutan milliwatt. Power dalam sebutan milliwatt. Okay.
Okay, Doctor. Thank you.
So in order to avoid confuse, remember that if we the purpose of we divide with the reference value is that we want to convert everything in the bracket either as milli, micro, or pico, or whatever. Okay, tujuan kita bahagikan dia kepada reference value is that we want to make it in term of specific unit, either in watt, milliwatt, or in microwatt. So that's why when we do direct conversions of anti-lock, okay, when we do direct conversions of anti-lock for the dBm, we will get in term of milliwatt. Okay, if we do direct conversions of anti-lock for the dB micro, we will get the value in term of microwatt. Okay, if we do direct conversions of dBw, we will get the value of watt. Okay, so this one I get 1.9938 milliwatt. Okay, ataupun 2 milliwatt. Okay, so is it true about this? Adakah ini betul? Okay, so let's compare with this one. Okay, let's compare with this one. So okay, so this one so I can assume this one as 2 milliwatt. Okay, saya assume dia adalah, untuk saya nak memudahkan pengiraan saya, okay, let's say it is a 2 milliwatt for example. So if I want to convert into dBm, P out into dBm, so this is 10 log of 2 milliwatt divided with 1 milliwatt. Okay, so I get this one in term of 3 dBm. Semua boleh dapat? Boleh 3 dBm, or it is actually 3.01 okay, dia 3.01 sebab tadi saya bundarkan so I assume a 3 dBm. Okay, so 3 dBm is the same as this one. So jawapan yang kamu kira adalah betul 3 dBm. Here also we get 3 dBm. Okay, yang tadi of course betul this one A total of course because we convert one by one and then we do the multiplication process, so we get this one 199.382. Okay, so if it is equal to 3 dBm, that means the answer is correct, same as previously. Kita dapat jawapan yang sama semasa kita buat dalam sebutan dBm. So this is just to check this is just to check. Okay, okay, so I think we answer the questions we answer the example. Okay, ada soalan lain nak tanya? Do you have any questions you want to ask about this?
Doktor, saya nak tanya.
Yeah.
Untuk milliwatt tu, maksudnya dekat nombor 2 tu kita boleh check sama ada result dekat kira-kira dBm tu sama ada betul ke tak maksudnya.
Which one? This one? Is it this one?
Yang nombor 2 ni lepas 2 milliwatt, then kita boleh dapat 3 dBm, maksudnya kita boleh check result sama ada kita kira dekat nombor 1 tu betul ke tak, macam tu.
Because kalau kita buat dalam sebutan dBm, sepatutnya dia mesti sama dalam sebutan watt. So itu sebab tadi untuk soalan yang kedua, saya dapat lebih kurang approximately 2 milliwatt although the value is 1.9938. Okay, it doesn't matter if you want to stick to this value, no problem. Okay, kalau kamu nak kekalkan nombor ini tidak ada masalah. Okay, ini saya buat approximately 2 milliwatt because I just want to check whether this value is the same as 3 dBm that I get previously. Saya cuma nak bandingkan adakah jawapan yang saya buat tadi betul atau tak. Dia sepatutnya mesti sama. Okay, in the first question I get 3 dBm. So I should get a conversion of this if I do the second questions. Okay, so that's why saya
Thank you,
buat
Doctor.
I just do a simple checking, simple calculation for checking. I just want to know is this correct or not. Okay, so I buat 10 log of this one, so I get 3 dBm. So this is the same as the first question, so it is a correct. Okay, kalau you dapat
Alright.
4 dBm, so that means that the answer is wrong. Okay, something is wrong, somewhere is wrong. Okay, okay, kalau ada soalan lain boleh tanya. Kalau tak ada saya
Doktor,
ya, silakan.
boleh tengok balik jalan kira yang P-in convert di milliwatt.
You punya suara putus-putus ah. Boleh tengok yang mana? Yang ni ke?
P-in.
This one?
Oh.
Okay.
Okay, doktor.
Ada lain soalan? Kalau ada boleh tanya no problem. So you can always interrupt me. I will try my best to answer your questions. Okay. Tadi pelajar yang bertanya, don't worry, saya ada rakam lecture video pada hari ini So katalah you terlepas pandang yang tadi, so you boleh lihat semula video yang saya akan upload dalam YouTube. Okay. Okay, so saya akan proceed dengan slide berikutnya. Ini ada dalam author. This is about dBm. Okay, this is the second file that I put inside the author about dBm calculations for chapter 1. Okay, so this is done by Dr. Hairun Nizam previously. So how to calculate the absolute ratio dB, dBm, dBw. Okay, ini ada dalam author saya telah masukkan dalam author. Okay. So about the conversions, so this is just examples. These are good examples to make to show to the students in order to understand the concept of dB. Okay, so convert the following power gain values into absolute ratio. So 10 dB, 0 dB minus 10 dB. Okay, so how to convert this into absolute value? So the first one, 10 dB. Okay, so see the first one. Okay, so 10 log A, you get 10 dB. You divide with 10, you get log A is equal to 1. And then anti-log of 1, you will get 10. Okay, so the bracket here show gain. That means this is a positive value. That means this is more than 1. So if the value is more than 1, that means it is a gain. Okay, and then 10 log A, so equal to 10 dB. So ini yang tadi yang ke 0 dB. So how to convert this into absolute value? 10 log A is 0 dB. Divide with 10, so you get 0. Okay, and then anti-log of 0, you get 1. This is in terms of absolute value. Tidak ada unit. And then 10 log A, you get minus 10 dB. Divide with 10. Okay, you divide this with 10, so you get minus 1. And then anti-log of minus 1, you get 0.1. So the value here is less than 1. So what we have learned previously, if the value is less than 1, it is attenuation or losses. Okay. And then convert the following. Okay. So now we have unit. Previously, we don't have unit. Okay. Previously, we produce a value. Okay, we produce 10, a value without unit. We produce 1. This is a value without unit. 0.1 is a value without unit. It's a unitless value. Okay, unitless parameter. Okay, dia adalah satu parameter yang tidak mempunyai unit. Okay, so now kita nak lihat macam mana kalau dia ada unit power. Okay, so this is about power. So power convert into dBm. So how to do this? Remember, if you want to convert into dBm, so what we need to do is 10 log power divide with the reference value of 1 milliwatt. Okay, so we're gonna get power in terms of dBm. Okay, so convert 1 micro, 1 milli, and 1 watt. So the first questions here. Okay, so 10 log, see the first question here, 10 log 1 micro, this is 1 microwatt, divide with the power reference 1 milli, because we want to change into dBm. That's why we divide with 1 milli. Okay, so 10 log 1 micro divide with 1 milli, so it is 10 log 1 milli, so it is a negative 30 dBm. Okay, remember, first of all, you need to solve the value inside the bracket. Barulah you buat, and then you do the logarithmic process. Okay. The second questions, 10 log of 1 milli. Okay, divide with the reference value 1 milli, because you want to convert into dBm. Okay, so 1 milli divide with 1 milli, so you get 1. 10 log 1 is 0, but the value is dBm. Okay, the third question. Okay, third question, 10 log 1 watt. You want to convert into dBm, so you need to divide with the reference value 1 milli. Okay, reference value 1 milli. So it becomes 1000. 1 divide with 1 milli, you get 1000. So 10 log 1000, so you get 30. But the unit in terms of dBm. Okay. Next, convert the following from dBm to milliwatt. Minus 30, 0 dBm, 30 dBm. So tukar kepada milliwatt. So how to do this? Okay. So you see that from here, 10 log of power. So the power in term of milliwatt. Okay, power in term of milliwatt equal to minus 30 dBm. Okay, so everything here inside the bracket, okay, is considered as in term of milli, because here we get dBm. Okay, so semua dalam bracket ini dalam milli, kerana dia adalah dalam sebutan dBm. Okay, so 10 log P in milliwatt, you get minus 3. Okay, minus 3. And then anti-log of minus 3, you get 10 power of minus 3, which is milliwatt. So dia adalah jawapannya 1 kali 10 kuasa negatif 3 milliwatt. Okay, dia ada milli kat sini. Walaupun sini you ada negatif 3, so walaupun over here you get a minus 3, but the unit must be in term of milli. Remember that. So it is actually like this, 1 multiplied 10 power of minus 3. Sorry, my stylus, minus milliwatt. Okay. Okay, go to the next questions. 10 log power in bracket must be milli equal to 0 dBm. Divide with 10, you get 0. So P in power in milliwatt, you get 10 anti-log of 0. Anti-log of 0, you get 1. But the unit in term of milliwatt. Okay. The third question, 10 log power in milliwatt. 10 log power in bracket here must be in milliwatt because here is dBm. Okay. So log power in milliwatt, you get 3. Okay, and then anti-log of 3, okay, anti-log of 3, you get 1000. So this is actually 1000 milliwatt. Okay, 1000 milliwatt. Okay. Next. If you have question, just interrupt me. You can ask question. Okay, so I proceed with the next slide. Convert the following power values to dBW. Okay. So you want to convert 10 watt, 1 watt, and 1 kilowatt. So this is a dBW. That means you do 10 log power, you divide with 1 watt. Okay, so the reference value is in terms of 1 watt. So 10 log 10 divide with 1, so we don't need to put 1 over there. Okay, so untuk memudahkan so dia letak 10 saja senang. So because everything is in terms of watt, and kilowatt. Okay, so 10 log 10, you get 10 dBW. 10 log 1, 0 dBW. And 10 log 1000, 10 log 1000, you get 30. But this one in terms of dBW. Okay. The next one is to convert from dBW to watt. Okay, to convert dBW to watt. So here we have 10 dBW, 0 dBW, and 30 dBW. Okay, so 10 dBW, we want to convert into watt. That means we need to do anti-log of this. Okay, so anti-log of dBW, we're gonna get the value in terms of watt. Okay, so 10 log P in bracket here. Okay, so we get 10 dBW. So the power here must in the bracket must be in term of watt. Okay, the value here must be in term of watt. Why in term of watt? Because here is dBW, dB watt. Okay, so 10 log power in watt, you get 1 because you divide with 10. Okay, you divide with 10. Here can be cancelled out. Okay, you divide, you get 1. So power in term of watt, anti-log of 1, you get 10 watt. Okay. Second question is that 10 log power in watt, we get 0 dBW. Okay, so anti-log of you divide first. You need to divide with 10, so you get 0. So log power equal to 0. Power equal to anti-log of 0. Anti-log of 0, you get 1. The unit in term of watt. Third questions, 10 log power equal to 30 dBW. Okay, we want to convert into watt. Okay, so log power in watt, so we get 3 because we divide with 10. So power equal to 1000 watt. Okay, so anti-log of 3, you get 1000. Okay, this is 1000 watt. Combined power in log scale, this one. So here you see that a simple example about power calculations. So this is very simple summation process. 1 watt plus 1 milliwatt plus 1 milliwatt. Nah, ini kalau you tambah, you do the direct summations, you get 2 milliwatt. Simple. Okay. However, you cannot do like this. Okay. You cannot just plus both of this. This is not allowed. Okay, dia tidak boleh direct summations. You cannot do direct summation. Okay, so what you need to do? You need to convert into power first, and then you can convert back into dBm. Okay, dalam case ini, if it is a dBm plus dBm, you need to convert into power, and then you convert back into dBm. Okay, so this is not allowed. So therefore, you need to convert into power. Okay, anti-log of 0 dBm. Okay, anti-log of 0 dBm, you will get 1 milliwatt. Okay, so 1 milliwatt and 1 milliwatt. Okay, so if you convert 0 dBm, you get 1 milli. Okay, anti-log of 0, you get 1, but the unit is milliwatt because this is milli. Okay, so back to the equations. 0 dBm plus 0 dBm is actually equal to 1 milliwatt plus 1 milliwatt. It is equal to 2 milliwatt. So 2 milliwatt, if you want to convert into dBm, okay, 10 log 2. Okay, ini sebenarnya dia gini So this 2 is actually 2 milliwatt divide with reference 1 milliwatt. Okay, so that's why this the example just use the value of 2. Okay, so 10 log 2 is equal to 3.01, but the unit must be in terms of dBm. Boleh Okay. Contoh yang lain. Nah, this example is allowed. Okay, 0 dBm plus 3 dB. So you will get the value 0 plus 3, you get 3, but the unit follow this one, dBm. Kenapa macam tu? Why is it like that? I show you example. Okay, so let's say this is 10 watt. You multiply it with 10. Ini berapa? 100
watt.
100 watt. 100 divide, sorry. This I just want to show you the difference. What about 10 multiplied with 10? How much you get? This is 100. No unit. Okay. So as I mentioned previously, that multiplication process in absolute value is equivalent to summation process in decibel. Okay. So here 0 dBm, this is in terms of power. Okay, this is in terms of power. And 3 dB here is a value without unit. Okay, this is power. Okay, power multiplied with a value without a unit. So it is like this example. Okay, dB plus dB, you can do it. Okay, kalau dB x dB plus y dB, you will get z dB. which is like this. Okay, dalam case ini we cannot in this case we can do direct summations because one is in terms of power, another one is a value without a unit, so we can do direct summation. Berbeza dengan yang tadi kerana yang tadi adalah power dan power yang dalam slide yang sebelum ini this one is different because this one is in terms of milliwatt. You need to multiply it with another power in milliwatt, which is wrong because we cannot do multiplication like this. Okay, dia akan jadi square power. Okay, so what we need to do is to convert into power. We do the summations and then we get the value and then we convert back into dBm. Okay, dia berbeza dengan yang ini kerana ini kedua-duanya dalam bentuk power. Okay, dalam sebutan milliwatt. Okay, let's look at the next example. Okay, so this allowed. What about this one? And then this is not allowed. Okay, this is not allowed for direct summation. Okay, tambah terus tidak dibenarkan. In this case, because this is in terms of millipower, milliwatt, so you need to change into power first. You do the summations and then you convert back into dBm. Okay, so the first one you convert 0 dBm. Okay, 10 log power milli because this is milli. You divide with 10, you get 0, and then power in terms of milliwatt, anti-log of 0, you get 1 milliwatt. Okay, 1 milliwatt. Untuk conversion, for the conversion of 0 dBm. For the conversion of 5 dBm, okay, for the conversion of 5 dBm, 10 log power in milliwatt, you get 5 dBm. Okay, so this is must be in terms of milli. So divide with 10, you get 0.5, and then anti-log of 0.5, you get 3.1623, but the unit must be in terms of milliwatt. Okay, so now you need to do the summation. 0 dBm plus 5 dBm is equivalent to 1 milliwatt from here plus 3.1623 milliwatt. So you get 4.1623 milliwatt. So from here, you can convert into dBm. So 10 log 4.1623 milli divide with reference 1 milli. So you can cancel out milli and milli. So you get 4.1623. So 10 log of this, you get 6.193, but the unit must be in dBm. Okay, because the reference value is 1 milli. Okay, kerana reference value-nya adalah 1 milli. Zero dBm plus 0 dBw. Also, this is not allowed because this is power in milliwatt, this is power in watt. You cannot do direct summation. You must convert into power. Okay, so what you need to do is do the conversions here. 0 dBm. Okay, so 0 dBm convert into watt, so you get power in terms of milliwatt. Okay, anti-log of 0. Okay, anti-log of 0 you get 1, but the unit must be in milliwatt because this is dB milli. Okay, kerana dia adalah dB milli. And then conversions of 0 dBw. Again, you see that 10 log of power, everything in the bracket must be in watt. Okay, must be in watt because here is dBw, dB watt. Okay, divide with 10, you get 0. And then anti-log of 0, you get 1. but this one must be in term of watt, because we convert from dBW. Okay, then you can do the summation, direct summation. So 0 dBm plus 0 dBW is equivalent to 1 milliwatt plus 1 watt. So 1 milliwatt plus 1000 watt. Oh, sorry, 1000 milliwatt. So it depends. You want to convert into watt or you want to convert into milliwatt? You have the options. Okay. So here, 1 watt is equal to 1000 milliwatt. Okay. So 1000 milliwatt plus 1 milliwatt. So you get 1001 milliwatt. Okay. So convert into dBm, 10 log 1001 milliwatt divide with the reference 1 milli. Okay, this is a milliwatt. Divide with 1 milliwatt. So you get 30.0043. The unit must be dBm because we divide with reference 1 milli. Okay. What about if you want to convert into dBW? 10 log 1001 milli divide with 1 watt. Okay, so this is 1001 milliwatt or 1001 multiplied with 10 power of minus 3. So this is what, this is what. Okay, so you cancel out. Okay, so here is 1001 multiplied with 10 power of minus 3 divided with the reference 1 milli. So you get 0.0043 unit is dBW because we divide with 1 watt as a reference. Okay, the reference here is 1 watt, so you get dBW. Okay, so which one? The answer can be this one. Okay, the answer can be dBm, or the answer also can be dBW. It's up to you. Depends on the question. The question asks in terms of dBm or dBW. Okay. So because the question asks in dBm and dBW. Okay. So the question asks both. Find the value in dBm, find the value in dBW. Okay. Okay. Ada soalan nak tanya? Do you have any questions to ask? Eh,
Tak ada doktor.
Okay. So we have complete chapter 1. Okay, kita telah selesai chapter 1. And I want to move to chapter 2. Okay, I will proceed with chapter 2. So students, if you want to take a break, you can take a break on for yourself. But I will proceed. Okay, saya akan teruskan. Tetapi kalau you nak berehat, you boleh berehat. You boleh pergi ke toilet, you can go to drink some water. Okay, if you want to take breakfast now, you can take breakfast. No. Okay, but for me, I will proceed with the next chapter. Okay, saya akan teruskan. Okay, okay, for later for attendance, I will take make sure you are in front of the computer between 10:30 to 11. Okay, 10:30 to 11 I will take the attendance. So for now, if you want to go for a rest, you can go for a while, no problem, and then you can come back here. Okay, So chapter 2 is about the noise. Bunyi gangguan noise is gangguan kepada signal yang dihantar. Okay, it's a disturbance to the transmitted signal. Okay, so the noise can degrade the quality of the transmitted signal. Okay, noise ini dia akan mengganggu kualiti signal yang telah dihantar. Okay. Sama juga macam sekiranya kita contoh saya bercakap dalam kelas dan sekiranya ada ramai pelajar yang buat bising, so that one is also noise that disturbs my noise. Okay, itu satu contoh kalau pensyarah mengajar di dalam kelas tetapi ada banyak pelajar yang buat bising, maka itu juga mengganggu suara daripada pensyarah yang mengajar. That one, it will degrade the quality of the voice. So pelajar yang duduk di belakang mungkin tidak dengar suara pensyarah di depan. Okay, that one is an analogy of the noise. Okay. So topics covered in chapter 2, we have types of noise, noise spectral density, signal to noise ratio, noise factor and noise figure, Friis formula, equivalent noise temperature, and also the noise measurement. Okay. And the core topics in chapter 2 is about this one, SNR, noise factor, noise figure, and also the Friis formula. So these are the core topics in chapter 2. Okay. And this is the family tree of noise. Okay. So the type of noise, you see that here noise can be classified into correlated noise and also uncorrelated noise. Okay. So correlated noise, again, it is a non-linear distortions which can be divided into harmonic distortions and also intermodulation distortion. And then for the uncorrelated noise, we have external noise, the noise that exists outside from the system, outside from the transmitter and receiver, which is in the channel. And then we have internal noise, the noise that happens inside the system, inside the transmitter and receiver. So there are three here: short noise, transient time noise, and also the thermal noise. So in your syllabus, we will focus on the thermal noise, the noise that which is related with the temperature. Okay, noise that related with the temperature. And then for the external noise, the noise that happens outside from the system, we have atmospheric noise, extraterrestrial noise, and also man-made noise, impulse noise, and also the interference. For the extraterrestrial, we have a solar noise, and also the cosmic noise. Okay, so I will explain about all of this later. Okay, and for your information, a few semesters ago, we have asked a question in test about this picture. That one is due before the COVID pandemic. We give a test question exactly like this. Okay, we give a box like this, and then students need to fill in the blank. Okay, pelajar perlu mengisi apakah jenis-jenis noise. Diberikan gambar rajah seperti ini, yang mana beberapa kotak dikosongkan. Pelajar perlu mengisi. Student needs to fill in what is the type of noise in the box. Okay, so but that one is a long time ago. Okay, but now it's an online test. We cannot do like that. Okay, so the question must be more difficult. Okay, tapi ini pernah keluar. I just want to tell you that ini pernah keluar dalam test. Okay, So now we want to look one by one about the noise family. Okay, so remember that the noise can be divided into two: correlated noise and also uncorrelated noise. So what is the correlated noise? Correlated noise is the noise that exists only when the signal is present. Okay, so correlated noise ini berlaku hanya sekiranya ada input. Okay, only when we have the input. For example, okay, for example, here is a transmitter. Okay, so if there is no input, okay, if there is no input here, that means out here there is no correlated noise. If there is input over here, for example, then it will produce correlated noise. Okay, it will produce correlated noise only when there is a input. Uncorrelated noise is the noise that will always present at all time, whether you have the input or whether you don't have the input signal. Okay, sama ada input signal atau tidak, uncorrelated noise sentiasa wujud. Okay, it will always present. Okay, regardless of there's a input signal or whether there's no input signal. Okay, and uncorrelated noise we can divide into internal noise and also the external noise. So for the external noise, there are three primary sources, which are the atmospheric noise, extraterrestrial noise, and man-made noise. So atmospheric noise is due to the electrical disturbance originate within the Earth atmosphere, commonly called as the static electricity. So this is the noise that due to the static electricity in the Earth atmosphere. Okay. So most static electricity is naturally occurring electrical conditions such as lighting. It is in the form of impulse, spread energy through wide range of frequency. So impulse is a short durations of signal. Is a short duration of high amplitude signal. Okay. Impulse bermaksud dia adalah dia punya masa adalah dalam masa yang singkat tetapi mempunyai amplitude yang besar. Okay, this is what we call as a impulse. Okay, so the noise, you see that the noise suddenly spike like this. So this is a impulse. Spread energy through wide range of frequencies. So if you have a wide range of frequencies, regardless of any frequencies, it will have this kind of noise. Okay, noise ini dia boleh berlaku dalam pelbagai jenis, pelbagai julat frekuensi. Dalam pelbagai julat frekuensi dia boleh wujud. So this kind of noise is insignificant at frequency above 30 mega. Okay, untuk frekuensi melebihi 30 mega, so this kind of noise is insignificant. Dia tidak ketara. Okay, tidak ketara. Extraterrestrial noise consists of electrical signal that originate from outside the Earth. Okay, in the deep space noise. It is also known as a deep space noise. Okay, so extraterrestrial noise can be divided into two, which is a solar noise. Solar noise is due to the sun activity, disebabkan oleh aktiviti matahari. Okay, solar noise can be divided into quiet conditions and also the sporadic disturbance. Quiet conditions when the constant radiation intensity exists and high intensity. Sporadic disturbance caused by the sunspot activities and solar flare-up when occurs every 11 years. Okay, so ini matahari itu seperti juga seperti something like gunung berapi yang mana dia ada masanya, yang mana dia akan lava panas itu dia akan flare ups. Okay, so this one happens in certain years. Okay, So matahari tu dia tidak statik, dia sentiasa mendidih, dia akan sentiasa seperti something like the gunung berapi, tetapi dia punya lava itu sentiasa keluar. So that's why it also produce a small noise, small amplitude noise, okay, due to the heat. And then a cosmic noise, continuously distributed throughout the galaxy. Small noise intensity because the sources of galaxy noise are located much further away from the sun. It is also called as the black body noise. Okay. Man-made noise, this is due to the spark producing mechanisms such as commutators in the electric motors, automobile ignitions, and etc. So this is also known as the industrial noise. Okay, the noise due to the human activities. Okay. Impulse noise is a high amplitude peaks of short durations in the total noise spectrum. So impulse noise, if you see that suddenly there's a spike over here, so this is a impulse noise. Okay, short durations of amplitudes, short duration of high amplitudes. Okay, so produced from electromechanical switches, electric motor, and etc. And then interference. So interference is also type of noise, but it is from the signal that has the same frequency as our signal. Okay, it occurs when the harmonics or cross product frequency from one source fall into the passband of the neighboring channel, usually occurs in the radio frequency spectrum. Okay, so this interference happens when you transmit at the same frequency with other sources. So for example, if you transmit at 1 megahertz, okay, and then another sources transmit at 1 megahertz also, so this will cause interference. Dia akan mengakibatkan interference. So if the interference happens, so what happens is actually, so when the interference happens, the receiver will have the difficulty to differentiate the original signal. Okay, receiver akan mengalami masalah untuk mengenal pasti sumber dari mana, ataupun dia sukar untuk menukar signal itu kepada original signal. Okay, the receiver will have the problem to convert into the original signal. The receiver will be unable to differentiate this kind of signal, whether this is from source number 1 or source number 2. And the received signal will be corrupted. Okay, so kira dia punya signal yang diterima itu akan jadi rosak kerana receiver tidak dapat untuk menukar ataupun untuk untuk differentiate this kind of signals. So you dapat output yang rosak. So you tak dapat nak produce the exact quality of the output. Internal noise generated within device or circuit. So these are the noise that happens inside the system, inside the transmitter or the receiver. The first one is a short noise, okay, caused by the random arrival of carriers, which are the holes and electron, at the output element of the electronic devices such as diode, field effect transistor, or bipolar transistor. The current carriers, AC or DC, are not moving in a continuous steady flow, as the distance they travel varies because of their random path of motions. So short noise randomly varying and is superimposed onto original signal. Okay, when it is amplified, the short noise sounds similar to metal pellets falling on a tin roof. Okay, so this is also known as the transistor noise. Okay, remember this is due to the random movement of the carriers. Okay, random arrival of the carriers, which is the hole and also the electron. Transit time noise. This is the noise due to the time taken for the carriers to propagate from input to the output. Okay, so the time it takes for the carrier to propagate through the device is an applicable part of the time, one cycle of the signal, so the noise becomes noticeable. So TTN is a transit is determined by the carrier mobility. Okay, disebabkan oleh pergerakan carrier, bias voltage, and also the transistor constructions. So the longer the time taken for the carrier to move from the input to the output, the higher would be the transit time noise. So this transit time noise is proportional to the time of the carrier movements. So the higher the time, okay, the longer the time, the higher would be the transit time noise. And then thermal noise, due to the rapid and random movement of electron within a conductor due to thermal agitation. Okay, ianya disebabkan oleh perubahan suhu yang mengakibatkan perubahan random electrons dalam conductor. Okay. It is uniformly distributed across the entire electromagnetic spectrum, often referred as white noise. Okay. Ini bukan noise putih. Maksud dia adalah regardless of the frequencies. Okay, regardless of the frequency, the thermal noise always exists. Okay, tidak kira frekuensi apa pun, okay, tak kira frekuensi apa pun, thermal noise ini sentiasa wujud. So this thermal noise is depending on the temperature. The higher the temperature, the higher would be the thermal noise. Okay. So it is a form of additive noise, meaning that it cannot be eliminated, and it increases in intensity with the number of device and circuit length. So lagi banyak jumlah device and lagi besar circuit itu, maka dia punya thermal noise akan semakin bertambah. Okay. So it is set as the upper bound for the performance of communication systems. So, kalau thermal noise ini tinggi, if the thermal noise is higher, the performance of the system becomes lower. So temperature dependent, random, and continuous occurs at all frequencies. Noise spectral density, ketumpatan noise. Okay, so this is noise spectral density. The unit is N0. Is the noise power per unit bandwidth. Okay, so noise spectral density is equivalent to noise power divided with the bandwidth. Okay, that is a noise power spectral density. So noise power spectral density is the noise power divided with the bandwidth. So the unit is watts per hertz. Okay, because you divide power with the bandwidth. Okay, you divide power over the bandwidth, so the unit is watt per hertz, which is equivalent to watt seconds, or you can say in terms of joules. Okay, so ada dua atau tiga unit di sini, watt per hertz, or you can say watt seconds, or you can say joules. Okay, so if the noise is white, remember this is not white in color, dia bukan warna putih, bukan White means it is spread across the entire frequency spectrum, regardless of whatever frequency, okay, it will exist. So it is constant with frequency. Then the total noise power, so the total noise power N in a bandwidth of B is B multiplied with N0. Okay, because N is equal to power Tadi dia guna sorry. So N noise power spectral density is equal to noise power N divided with the bandwidth. So noise power N dalam sebutan power in term of watt is equal to spectral density multiplied with the bandwidth, or B, Bw or B. Okay, dalam kes ini dia buat B, bandwidth. Okay, so I make it similar. So this is N over B. So N is N0 multiplied with B. So this is utilized in the signal to noise ratio calculations. Okay. So why it is so important? Because this is used in the SNR calculations. Okay, SNR calculation you will see later. So the thermal noise density is given by N0 equal to KT. Okay, so you can also write like this in term of temperature. Okay, either you want to write like this, N0 multiplied with B, sorry, this one, N0 equal to N divided with B, or you can write N0 equal to KT. So not only one equation, there are two equations about this, okay, for the noise power spectral density. So N0 is also equal to K multiplied with T, where K is a Boltzmann constant, the unit is Joule per Kelvin, and T is the temperature, the unit in term of Kelvin. So remember, temperature in your syllabus only use unit Kelvin, not Celsius. Okay, dalam syllabus kamu temperature digunakan dalam sebutan Kelvin. Okay, so N0 is commonly used in the link budgets as the denominator of the important figure of merits ratio, which is the EB over N0. This is the bit energy divided with the noise power spectral density, N0. Okay, so what is this? Okay, this is an important parameter. This is similar with the SNR in the analog. Okay, in the digital system, this is more important rather than the SNR. Okay, kita dalam analog system kita biasa cari SNR. Okay, signal power divided with the noise power, SNR. But in the digital system, we use EB over N0, bit energy divided with the noise power spectral density. Or we can also find the symbol energy, ES, divided with the noise power spectral density. So both of these are the important parameters in the link budget analysis. The digital system. Okay, dalam digital system kita menggunakan parameter ini. So you will see both of these in chapter 4 later. Okay. Okay, noise power. So how to calculate the noise power? So noise power Pn or N. Okay, you boleh tulis Pn or N. And if you want to write just N, is also okay, no problem. Okay, equal to integral from minus B to B. Okay, because it is depending on the bandwidth. Okay, so if let's say this is a frequency and this is the frequency band. Okay, so this is minus B until B. So how much is the noise power inside the bandwidth? Okay, so it is equal to N0 multiplied with B, or you can also write it as KTB. So you need to know, or you need to memorize these equations. This is a very important equations. The noise power equal to K, which is the Boltzmann constant, multiplied with the temperature in Kelvin, multiplied with the bandwidth in Hertz. Okay, so Boltzmann constant 1.38 multiplied with 10 power of minus 23 joule per Kelvin. T is the absolute temperature. So if it is a room temperature, it is a 17 degree. So room temperature in your syllabus is not 25 degrees Celsius. It is actually 17 degrees Celsius. Okay, by default, room temperature. Ni biasanya normally we will give the noise temperature in the test and also in the final exam. Okay, so if the question gave you different room temperature, so it depends on the room temperature. It depends on the questions. Okay, but in your syllabus, I just want to inform you that in your syllabus, the room temperature is 17 degrees Celsius. Sejuk agak sejuk. Okay, so 17 degrees Celsius is equal to 290 Kelvin. So how to get this value? Okay, so the way to convert from Celsius to Kelvin. Okay, so you need to x plus 273. Okay, you will get a value in term of Kelvin. Okay, so this one 17 plus 273, you will get 290 Kelvin. Okay, remember all calculations must be in term of Kelvin. Kita akan menggunakan unit Kelvin sepenuhnya dalam syllabus, dalam kamu punya syllabus. Okay, don't use Celsius. Jangan gunakan Celsius temperature. Don't use that. You need to use Kelvin only. Okay. And you see that it is clear that the power spectral density of thermal noise increase with the increasing of ambient temperature. Therefore, keep the electric circuit cool makes the noise level low. So that's why this is one of the reasons that we need to keep our electronic device in a cool place. Okay, ini salah satu sebabnya kenapa kita perlu letakkan atau kita perlu simpan kita punya peralatan elektronik dalam tempat yang sejuk. Okay, this is one of the reason. The noise voltage. Okay, so the noise voltage Vn. Okay, the noise voltage Vn, which is seen from the load. Okay, at the load side. Okay, so for example, here is the noise source. Okay, we have the circuit like this. Okay, Vn, and then this is a Ri, R internal, and we have a resistor which is connected in series with the load resistor. Okay, so this is a load resistor. So you see that for the worst, the internal resistance is in series with the RMS noise of the noise voltage Vn. Okay, so this one is in series. For the worst condition, the load resistance R is equal to Ri. Okay, so if R over here equal to the R internal, it will produce the worst conditions of noise voltage at the load. Okay, the noise voltage drop across R load at the load is half the noise source. So V voltage at the load is equal to Vn over 2. Okay, ini adalah berdasarkan Ohm's law. And the noise power Pn developed across the load resistor is KTB. So the load here. Okay. So Pn over here is equal to KTB. So which is Vn over 2 square divided with R. Remember Vn in terms of RMS. Okay, Vn here is RMS. So that's why we divide with 2n square, divide with R. Okay. So, and then we get Vn square over 4R. Okay. So Vn square for R is equal to KTB. Okay, Vn square over 4R is equal to KTB, so Vn square is 4R KTB. Vn is equal to square root of 4R KTB. So this is the noise voltage formula. I suggest you to memorize these equations. This equation is derived based on this circuit. Okay, based on this simple circuit during the worst conditions. Okay, so this is in terms of RMS voltage. Example. Okay, calculate the thermal noise power available from any resistor at the room temperature 290 Kelvin. Okay, for a bandwidth of 1 megahertz. Calculate also the corresponding noise voltage given R50. So you have a R50. Okay, so how much is the noise? Okay, thermal noise power. So thermal noise power is KTB, K 1.38 multiplied with 10 power of minus 23. Okay, so multiplied with the temperature multiplied with the bandwidth. Okay, the bandwidth is given as 1 mega. So you get 4 times 10 power of minus 15 watt noise power. Okay, and then how much is the noise voltage across the given R? Okay, given the value of the resistor is given as 50 ohm. So how much is the noise voltage? So noise voltage is equal to square root of 4R KTB. So 4 times resistance 50 ohm times KTB. KTB we already get from here, which is 4 times 10 power of minus 15. So you get the value 0.893 microvolt. Okay, very straightforward. Example 2.3, for an electronic device operating at temperature 17 degrees Celsius with a bandwidth of 10 kilohertz, determine the thermal noise power in watts and dBm. So therefore, you need in order to calculate the noise power is KTB. Okay, K times T times B. So 1.38 times 10 power of minus 23 multiplied with the room temperature, which is 290. So you must convert this into Kelvin. So you need to plus with 273. 17 plus 273, you will get 290, 290 Kelvin. Okay. Multiplied with the bandwidth. So the bandwidth here is 10 kilohertz. So that's why you multiply it with 10 kilo. So you get 4.002 power of minus 17 watt. And then convert into dBm, 10 log power divide with the reference value 1 milli, because we want to convert into dBm. So we get negative 134 dBm. Okay. And then RMS noise voltage for a 100 ohm internal resistance and 100 ohm of load resistance. Again, if you draw the picture like the previously, so you have the internal noise and then internal resistance, and then you have the load resistance. Okay, so this is a noise source. So remember that we take the load resistance, which is a 100. Okay, we don't need to summarize. We don't need to sum both of this value. Okay, kita tak perlu tambah kedua-dua sebab kita merujuk kepada load resistance. Okay, we refer to the load resistance. So the RMS noise voltage at the load. Okay, so it is equal to square root of 4R KTB, square root of 4 multiplied with R is 100 ohm for the load resistance, multiplied with KTB. KTB we get 4.002 times 10 power of 17. So we get 0.127 microvolt in RMS. The next example is example 2.4. Two resistors of 20K and 50 kilo ohm are at room temperature 290 Kelvin. Okay, so you might wonder why we use a room temperature 290. So this is based on the Wayne Thomas's book. Kalau kita berada di Malaysia, kita punya suhu bilik biasa kita letak 25. For your syllabus, because we based on the Wayne Thomas's book, so the room temperature is 290 Kelvin. Okay, for a bandwidth of 100 kilohertz, bandwidth of 100 kilohertz, calculate the thermal noise voltage generated by each resistor. Okay, so you need to calculate the thermal noise voltage for 20K kilo ohm and also 50 kilo ohm for each resistor. So you need to calculate one by one for the first question. Okay, so for the first questions, you need to calculate the noise voltage for the first resistor. Okay, 20 kilo ohm resistor. So 4R1 KTB, square root of 4R1 KTB, square root of 4 times 20 kilo ohm multiplied with 1.38 times 10 power of minus 23. This is the Boltzmann constant multiplied with the room temperature multiplied with the bandwidth. So you get 5.66 times 10 power of minus 6 volts. Okay. And then for the second resistor is square root of 4R2 KTB, square root of 4 multiplied with the resistance 50K, Boltzmann constant multiplied with the room temperature multiplied with the bandwidth. So you get 8.95 times 10 power of minus 6 volt. The second question said that you need to find the thermal noise voltage if the two resistor is in series. Okay, if the two resistor is in series, that means you need to sum both of the resistor. Okay, so the resistor is connected in series, R1 and R2. So therefore R total, you need to find the R total is R1 plus R2 for the R total. Okay, so 20K plus 50K, so you will get 70 kilo ohm. And then you find the noise voltage, square root of 4R total KTB, square root of 4 times 70 kilo ohm multiplied with the Boltzmann constant multiplied with the room temperature multiplied with the bandwidth. And then you get 1.06 times 10 power of minus 5. Okay, and then the third question said that find the noise voltage for the if the two resistor is connected in parallel secara selari. Okay, so if the two resistor connected in parallel, so you need to find the um, R total. Okay, so R1, R2. Okay, so R total is equal to 1 over R1 plus 1 over R2. Okay, inverse. So you get 14.28 kilo ohm. Ini you boleh cuba kira. Okay. Ini saya tulis balik. So saya harap kamu pun boleh tahu cara kira dia. So sekejap saya buat balik, saya tulis balik. So R total equal to 1 over R1 plus 1 over R2. Okay, and then inverse this one. So you get 14.28 kilo ohm. Okay, so the R total for the parallel connections, you get 14.28 kilo ohm. So put inside the equation square root of for RKTB 4 times R total times K Boltzmann times room temperature times the bandwidth. So you get 4.78 microvolt. This is for the parallel connections. Okay. So if you have question, you can ask me anytime, no problem. Okay. Okay, now so we have seen about the uncorrelated noise in the previous slides. Now let's look at correlated noise, the noise that only present when there is a signal. Okay, noise yang berlaku sekiranya ada input signal. So correlated noise we can divide into two, okay, which is the first one is harmonic distortion. So harmonic distortions happens due to the unwanted harmonics of a signal produced through nonlinear amplifications, or you can say through nonlinear mixing. Okay, so harmonics are integer multipliers of the original signal. Okay, so secara mudahnya kalau kita lihat, we have the input signal, and when this input signal is mixed up with, if this single input signal is put inside the nonlinear amplifications, it will produce a small harmonic. Harmonic yang kecil, beberapa harmonics. It will produce some harmonics. Okay, very small amplitudes of noise. Okay, dia menghasilkan noise pada amplitude yang kecil, which is what we call as the harmonics. Okay, so there are various degrees of harmonic distortions, second order, third order, fourth order, sixth order, and many. Okay, and please correct, this is supposed to be HD. HD stands for harmonic distortion. Okay, so second order HD ratio of RMS of the second harmonic to the RMS amplitude of the fundamental. Okay, so this is the fundamental. If you see from my picture, this is the fundamental, the input, the original signal, and the second order, the next is second order, third order, fourth order, fifth order, sixth order, until the n order. Okay, so we will see the calculations later. And then if we sum all the harmonic distortions, we get the total harmonic distortion, THD. Okay, ratio of the characteristic summation of the RMS value divide with the fundamental value. So how to calculate this one? Okay, so this one, okay. So let's look at this picture A, for example. So harmonic distortion is based on picture A. So we have a single input. Okay, we have the single input here, and through the nonlinear amplifications, through the nonlinear mixings, it will produce harmonics, which is V2, V3, and also the V4, which is located at 2F1, 3F1, and 4F1 locations. Okay, dia berada pada frekuensi 2 kali F, 3F, 4F, 5F, 6F, dan seterusnya. Okay, so the second order, okay, if you want to calculate the second order HD, it is equal to V2 divided with the V1. This is a second order. Okay. Third order, okay, third HD. Third HD is equal to V3 divided with V1. Okay. But we can also write in terms of percentage, we multiply it with 100%. If you want to make it in terms of percentage. Okay. So we can write here multiplied with 100% if you want to make it in terms of percentage. Okay. For fourth degree harmonic distortions is V4 divided with V1. If you want to make it in terms of percent, we multiplied with 100%. Okay, so this is for the fourth order harmonic distortions. Okay, and for the total harmonic distortions, we can calculate by quadratic summation divided with the fundamental. So quadratic summation is V2 square plus V3 square plus Vn square. So we have the quadratic. So V higher is the quadratic summation. Okay, quadratic summation. Okay, quadratic summation. So and then we divide with V1. Kita dibahagikan dengan V1. Okay, so nanti ada contohnya. So that means this one, if I rewrite this one, so THD is equal to quadratic summations. Okay, V1 square plus V2 square plus until Vn square. Okay, divide with V fundamental, which is V1. And then you can multiply it with 100%. So we can find it in terms of percentage value. So the value is X in terms of percent. Dalam sebutan peratus. Okay. And then intermodulation distortion, the second type of correlated noise. Okay. So intermodulation distortion is the generation of unwanted sum and difference frequency. So it is the generation of unwanted sum and different frequencies when two or more input signal are amplified in a non-linear device such as large signal amplifier. Remember that for the harmonic distortion, we only have single input. But here, intermodulation distortion, we have at least two input signal. Okay, combined together, mixing together in a non-linear device. So it will produce intermodulation distortions. So remember, intermodulation distortions is happen when at least we have two or more input signal. Okay, so the sum and difference frequencies are called the cross product. So I show the picture. The picture is picture B. So in picture B, it shows at least we have two input, V1 and V2. Okay, you put this together inside the nonlinear device, nonlinear amplifications. So what happens is that it will produce harmonics. And the main harmonics is what we call as the sum and difference. Okay, so sum is the F1 plus F2, and the difference is located at F1 minus F2. Okay, so we call it difference because it is located at the lower side frequency. We call it sum because it is located at the upper side frequency. Okay, so this F1 is the input, F1, F2 is the input. So the difference, V difference is located at F1 minus F2. V sum is located at F1 plus F2. And remember that we also have another harmonics as well. Okay, dia ada beberapa harmonics lagi sebenarnya. Okay, we also have a few sets of harmonics. But the main thing here is the sum and difference. Okay, so figure B, I already showed the figure B. So mathematically, the cross product is equal to MF1 plus minus NF2. Okay, where F1 and F2 are the fundamental frequencies, and F1 more than F2. Okay, M and N is any positive integers between 1 and infinity. Boleh sebarang nombor antara 1 hingga infinity. Okay. Let's look at the example. Determine the second, third, and 12th harmonics of 1 kilohertz repetitive wave. Okay, so how to do this? So the fundamental frequency is 1 kilohertz. So therefore, the second harmonics. Okay, so the first question asks, where is the location? Okay, the first question asks, where is the location of the harmonics? Di manakah kedudukan harmonics? So the harmonics for the second order located at 2 times the fundamental frequency. So 2 times 1 kilohertz. So the second order located at the 2 kilohertz. Third order harmonics located at 3 times the fundamental frequency. So 3 times 1, we get 3 kilohertz. So third order harmonic terletak pada 3 kilohertz frequency. 12th order harmonics located at 12 multiplied with the fundamental frequency. So we get 12 kilohertz. So the 12th order harmonic located at 12 kilohertz frequency. Ini di mana kedudukan dia dalam spectrum. Okay. The second question. Okay, second question. Calculate the percent. Okay, dalam sebutan percent of second order, third order, and also the total harmonics distortion for a fundamental frequency with an amplitude of 8 volt RMS, and a second harmonic amplitude is 0.2 volt RMS. Third order harmonics amplitude is 0.1 volt. Okay, so ada dua soalan yang ditanya. Okay, so second and third. Okay, so fundamental voltage is 8 volt. Okay, so dia suruh cari second, third, and also the total harmonic distortion. So how much is the second order harmonic distortion? So it is V2 divided with the V fundamental multiplied with 100%. So 0.2 divided with 8 multiplied with 100. So we get 2.5%. How much is the harmonic distortion for the third order? Okay, so V3 divided with V fundamental, V1, multiplied with 100%, so we get 0.1 divided with 8, multiplied with 100, so we get 1.25%. Total harmonic distortion. So this question asks total harmonic distortion up to the third harmonic. So don't confuse with the first question. The first question just asking about 12. So for the second question, it's only want you to calculate up to third order harmonics only. Okay, soalan yang ini dia cuma tanya sehingga third order harmonic sehingga third order. How much is the total harmonic distortion up to the third order? So equivalent to square root of 0.2, the second order, plus 0.1 square of the third order. Okay, and then you do the square root. Divide with a V fundamental, and then multiplied with 100%. So you get 2.795% for the total harmonic distortion. Okay, so remember we want the value to be as minimum as possible. Okay, kita nak nilainya lebih sekecil yang mungkin. The lower will be the better for the quality of the signal. Okay, because we try to minimize the harmonics, because the harmonics will always exist. Okay, harmonics ini dia akan sentiasa wujud. We can eliminate the harmonics using the filter. Okay, filtering process. Okay, example 2.6 is about the cross product for the intermodulation distortion. So here we have the two inputs. Okay, kita ada dua input, 3 kHz dan juga 8 kHz, 8 kHz. Determine the first three harmonics present in the output of each input frequency. So remember that these two frequencies will produce harmonics. Each of these frequency will produce different sets of harmonics. Okay, so the first question asks, where is the location of the harmonics due to the input? Di manakah kedudukan harmonik ini disebabkan oleh input ini? Okay, so the question asks up to 3 harmonics only. Okay, so therefore, see the first, this one. So since we have two frequencies, F1 and F2, okay, F1 8 kHz, F2 3 kHz. So where is the location of the harmonics? For the first frequency, 3 kHz, the first harmonic is located at, which is the original frequency. So normally we don't call the as a harmonic. It is a fundamental frequency. Okay, the first is what we call as a fundamental frequency, which is 3 kHz. Second harmonics, so now we can call harmonics. Second harmonics is 2 times original frequencies. So 2 times 3, you get 6. Third harmonic located at 3 times frequency. So we get 9 kHz. So these are the location of the harmonics. And then for the second input frequency, okay, which is the 8 kHz, fundamental is 8 kHz. Second harmonic is 2 times original, so 2 times 8. So it is located at 16. Third harmonics is located at 3 times 8, so 24 kHz. Okay, so these are the locations of the harmonics. A small amplitudes of noise. Okay, there are small amplitude of noise located at these frequencies. Okay, and then the second question is about the cross product. Okay, so calculate the cross product frequencies for value M and N, 1 and 2. So don't confuse with these questions. What it means is that M can be 1 and 2, N can be 1 and 2. Okay, so in this case, we have 4 combinations. Okay, we have 4 combinations. Sorry. Okay, we have 4 combinations. Either we want 1 and 1, 1 and 2, or 2 and 1, 2 and 2. Okay, dia akan ada 4 combinations. Okay, we're going to have 4 combinations because the value of M and N, 1 and 2. Okay, so therefore, remember cross product, MF1 plus minus NF2. And remember F1 must be bigger than F2. So F1 is 8, F2 is 3 kHz. Okay, so the first one, 1 and 1, okay, M1, N1, so 8 plus minus 3. So the cross product is located at 5 kHz and 11 kHz. 5 kHz we get 8 minus 3. Okay, 8 minus 3, we get 5. 8 plus 3, we get 11. So this is the difference frequency. This is the sum frequencies. Okay. And then M1 and 2. So 1 multiplied with 8, we get 8. 2 times 3, we get 6. So 8 plus minus 6. So the difference frequency is 2 kilohertz, 8 minus 6. The sum frequency is 8 plus 6. So 14 kilohertz. And then when M is equal to 2 and equal to 1, so 2 times 8, we get 16 kilohertz. 1 multiplied with 3, we get 3 kilohertz. So 16 plus minus 3. So difference frequency, we get 13 kilohertz. Sum frequency, we get 19 kilohertz. And then when M equal to 2 and equal to 2, so this one, 2 multiplied with 8, you get 16. 2 multiplied with 3 kilohertz, you get 6. So therefore 16 plus minus 6. So the difference frequency is 10 kilohertz. The sum frequency is 22 kilohertz. Okay. So these are the answers. Okay. So in order to answer this question, it is better to do a simple table like this. Okay, lebih mudah menggunakan table seperti ini. Okay. Okay, the next part is about signal to noise ratio, SNR. This is very important parameter in the analog system. Okay, so SNR is the signal power divided with the noise power. That means we want the SNR to be as much as possible. Okay, we want the value of SNR to be bigger. Okay, if the value of SNR is bigger, that means the signal power is much more stronger, much stronger than the noise power, which is better. Okay, kita inginkan SNR yang tinggi, sebanyak yang mungkin, setinggi yang mungkin value-nya. Okay, so SNR is a ratio. Okay, dia adalah ratio. For example, noise power, signal power divided with noise power. So it is a no units. This parameter has no unit because it is a ratio. And when we convert into decibel, the unit will be in terms of decibel. 10 log ratio, power ratio. Okay. So PS is the signal power. Signal power is our signal, our transmitted signal. Noise power is the noise that disturbs the transmitted signal. Okay, noise power adalah power daripada noise yang mengganggu signal yang dihantar. Okay. And then we can also calculate based on the voltage ratio. Okay, so 10 log Vs square over Vn square. Remember that power is equal to V square over R. Okay, V square RMS in divided with R. So this is Ohm's law. So that's why we divide SNR. So this is Vs square over R divided with Vn square over R. So both R is the same value, so we can cancel out. So that's why you see here Vs square over Vn square. Okay, so 10 log Vs square over Vn square. So the value of 2 here you can put in front. So 20 log Vs over Vn, V noise. Okay, V signal over V noise. Let's look at the example. Example 2.7. For an amplifier with an output signal power of 10 watt and output noise power of 0.01 watt, determine the S and R, S over N. Okay, this one. Okay, so it is an amplifier like this. Okay, so it is said that the noise power S equal to 10 watt. noise power is equal to 0.01. This one is at the output. Okay, so S over N, so 10 divided with 0.01, so you get 1000. No unit. Okay, so class students, no need to write this one. No need to write unitless. Just write 1000 is enough. Okay, because I saw many some students they write unitless in the exam. Okay, so tak perlu jangan tulis, tak perlu tulis. Kalau no unit, if no unit, then no need to put any unit. Just 1000 enough. Okay, and then in decibel, 10 log 1000, so you get 30 dB, 30 decibel. Okay, this is a straightforward calculations, easy. Example 2.8, for an amplifier with an output voltage of 4 volt and output noise voltage is 0.05 volt. Okay, so here if you draw the amplifier at the output, the signal voltage is 4 volt, the noise voltage is 0.05 volt. Okay, how much is the SNR? Okay, so again, this is V square over R, V divide with Vn square over R. So R can be cancelled out. So it is a Vs square, V signal square divide with Vn square. So you get 640,000. No unit. Okay. And when we write in terms of decibel, okay, 10 log S over N. Okay, so 10 log S over N. Okay, so 10 log 640,000. Okay, so you get 58 dB. Okay, so remember the way we calculate is 10 log. Okay, 10 log parameter, 10 log parameter. So since we already get the value 640,000, so 640,000 over here, so we get 58 decibel. Okay, this one. Okay, this topic is very important. Okay, very important. Noise factor and noise figure. Noise factor is a unitless parameter, no unit. Noise figure is a value, is a decibel value of noise factor. Okay, so noise factor F is equal to input signal SNR divided with the output signal SNR. So if you draw the amplifier, example of amplifier, okay, so we have the input over here, we have the output over here. Okay, the output. Okay, the output over here. So the input, at the input side, we have the S input and also we have the N input. At the output side, we have the S output and we have the N output. Okay, so we have the input SNR, which is equal to Si over Ni. We have the SNR output, which is So divided with No. Okay, so kita ada dua jenis SNR, at the input and also at the output. So this noise factor is the SNRI So the noise factor is SNR I divided with SNR O. Okay, and for the noise figure is the decibel value of noise factor. So 10 log f, you get the noise figure in decibel. Okay, so in a perfect system, f equal to 1, input sama dengan output, which is a perfect system. It doesn't exist in the real world. Okay, in the perfect system, NF is 0 dB. Okay, so we want the noise factor to be as close as possible to the value of 1. Kita inginkan noise factor ini kecil menuju nilai 1. Okay, because if F is equal to 1, it is a perfect system. Input sama dengan output, which is very good. Okay, so the higher the value of F, the higher would be the noise factor. The noise will be higher, which will degrade the quality of the transmitted signal. Remember, we want the noise factor to be minimum close to the value of 1. Menuju ke arah 1. Lagi kecil, lagi bagus. Okay. And here, okay, so I want to show this one for the a two scenario where we have the internal noise and without the internal noise. Okay, I will show based on this picture. Okay, so here is the ideal case. For the first one is the ideal case. Okay, so we have an input signal power, we have the input noise power, and here we have amplifier here has a gain AP, and the output here, the S output is AP times SI. Of course, we multiply with the gain. We multiply with the gain. Okay, output signal is equal to input multiplied with the gain. So APSI, and the noise power also will be multiplied due to the gain. Okay, so AP times the noise input. So therefore, if you see here, we can cancel out here and we get SI over NI. So that means input equal to the output. Okay, so the ratio is still SI over NI. Sama. SNR dia sama. SNR input equal to the SNR output. So the first one is, this is for the ideal case. In this case, F equal to 1. Okay, and F equal to 0. Perfect. But doesn't exist in the real world. Tidak wujud dalam dunia sebenar. Let's look at the second scenario where we have the internally generated noise, ND. And we have the gain over here. Okay, so we have input signal power, input noise power put inside a non-ideal amplifier. What happened is that output signal power is AP times SI. Okay, and then output noise, so something happened in the output noise. The output noise will be different. So you see that output noise is equal to gain multiplied with the input noise, and then you plus sum with the internally generated noise. Okay, so that means the noise, the total noise at the output is AP and I plus internally generated noise. This is the total, this is the output noise. So that means the output SNR is less than the input SNR because we have additional noise. Okay, dalam case ini, in this case, F more than 1. Okay, F more than 1. What if we have many amplifiers cascaded in a cascaded? Okay, we arrange in a cascaded way. Okay, we need to use the freeze equations. Ini nanti saya akan terangkan. I will explain about this next week. Okay, next week I will explain about for the noise factor and noise figure for the cascaded amplifiers. Cascaded amplifiers, we need to use the freeze equations like this. Okay, and I will explain this next week. Okay, so here is the case where non-ideal case. Okay, we have the uh, we have the gain and also internally generated noise. So I will explain this next week. So now I will take the attendance, so you can switch on your QR code reader, so we can take the attendance. Yeah. Okay, for the attendance. So we have a few minutes. If you want to ask question about project, you can ask me questions, no problem. So I hope that you already conduct first, at least you have first meeting, worst case scenario. The more meetings would be the better. Remember, when you conduct meetings, you need to have the minutes of meetings. You need to write down what you have discussed in the meetings, and you need to take picture of the meetings. Since you do the online meetings, so you need to take picture of your online meetings. Okay.
Doctor, I have
Yeah.
one question.
Yeah.
For project. In the proposal,
Okay.
what have we, I mean, apa yang perlu letak dalam proposal tu? Maksud saya.
Okay, nanti saya akan berikan dia punya format. In the proposal, you need to put the proposed block diagram, for example. Okay, and then you discuss about what you plan to do for the project, including the minutes of meetings. Okay, akan ada there gonna be a filler table. Okay, you need to put the filler table because filler is the planning process. Okay, ada filler table, and then you have the diagram, the block diagram of your proposed project. Macam mana you nak buat dia punya GUI, what is the functions, what is the function that you want to put inside the MATLAB, what is your expected output. Okay, dari segi output, you nak produce parameter apa, you nak produce what kind of graph you want to put. Okay, I'm not expecting you to have the codes. Okay, saya tidak expect you sudah ada codes ni. This is just a sketching of your planning. Okay, how you want to do the GUI, what is how the GUI will looks like, what is the function that you want to do inside the MATLAB, what is the output that you want to produce. Okay, what parameter you want to calculate, what graph you want to produce. That kind of things. It's a planning thing. Boleh? Adakah saya menjawab soalan? Nanti dia punya the details of the format I will explain to you later. Okay, I will give the formatting later.
Menjawab doktor.
Okay.
Cuma kan kita dapat contoh saya punya group dapat AM modulation and demodulation kan.
Okay.
I mean saya tak berapa nak faham about that topic. I mean how to do in
Yeah,
the
because that one is a chapter 3. That one you will learn in chapter 3. For AM, that means you have the input analog input signal, and then you have the carrier signal. So that means you need to put how much is the value of the frequencies, input frequency, input amplitudes or input power, and then how much is the value of the carrier, the frequency of the carrier, the power or the voltage of the carrier, and then during the modulation process, what is the output values, what is the graph at the output. So you have the input graph, okay, you have the input signal, carrier, and then you have the output graphs, and then the value of the output.
Doktor, kalau dah scan boleh keluar tak? Saya
Boleh,
test.
silakan. Siapa yang dah scan boleh keluar, silakan. Sorry.
Okay. Thank you, Doktor.
Okay, no problem.
Okay, doktor.
So,
Doktor, kalau meeting pun boleh doktor tolong tekan untuk attendance.
Sekarang you pakai apa? You tak dapat nak scan Siapa tak dapat scan? Siapa nama? Siapa?
Siti Sarah.
Siti Sarah? Siti Sarah dah?
Oh, dah
Dah.
tekan. Okay, thank you.
Nur Salwa juga doktor.
Siapa?
Doktor Nur Salwa Farhani. 37.
Oh, Nur Salwa, okay. Yang lain?
Doktor saya.
Siapa nama?
Tamender.
Starting from D.
THA.
THA, Tamender. Okay, Tamender, okay. Siapa lagi?
Saya Tan Kawang.
Okay, Tan Kawang. Okay. Lagi siapa belum?
Doktor.
Siapa nama?
Saya Muhammad Faris.
Okay.
Okey, terima kasih doktor.
Okay, sama. Siapa lagi belum?
Terima kasih doktor, terima kasih.
Semua dah Anybody?
Dah doktor, dah terima kasih doktor.
Okay, kalau dah saya tutup So ada dua orang absent. Dua orang absent adalah Norizan dan juga Denisha. Okay. So itu saja pada hari ini. So see you next week. Okay. Assalamualaikum and goodbye.
Thank you doktor.
Thank you, doktor.
Terima kasih, doktor.
Waalaikumsalam.
Doktor.
Okay.